Hey, what's up, everyone? Welcome to this last live stream of the year where we're going to talk about the craziest Swift code you will ever see. Before I show you what this live stream is about, I have one disclaimer. No, actually, two disclaimers for you. First one is that usually I try to show you content that is very useful. I try to maximize the usability of what I show you in the real world. This is not the case today. That's why I'm doing this before Christmas as kind of like a spin-off. I'm gonna show you something that is very interesting, really nice on the intellectual curiosity, but the chances that you use it in your day-to-day work are close to none. Or rather, if you find a way to use it in your day-to-day work, please let me know because I want to know about it. And then the content I'm going to show you, I'm going to base my live stream on an article that was written by someone who studied math in grad school, which I didn't. So it's going to talk about concepts in math that I've never formally studied. So be aware that in what I'm going to say, there will probably be approximations. Maybe, I hope, small mistakes. I hope not, but maybe big mistakes. So don't take my word for granted on all of the math-related content of this live stream because it's not something that I've studied formally. I have like an understanding of it, but that's where it stops. So let's actually get started. Let me show you what it's gonna be about. So we're going to talk about an article called Seemingly Impossible Swift Programs. You have the link in the description as always if you want to check out the article. And if you look at the name of the author, this might ring a bell for some of you. So I'm talking about Brandon Williams right here because Brandon Williams is one of the two authors of TCA, the composable architecture, and also one of the two hosts of the Point 3 series of videos. This article he wrote in 2018, so a bit more than 5 years ago as I'm doing this live stream. And I got the idea following my live stream on TCA 2 weeks ago to cover this article to finish the year because of all of the articles I've read about Swift, it's definitely one that I still remember 5 years after because it's about a content that is unlike anything you normally read in a Swift blog. So let's get started. Let's start to go down the rabbit hole. So in the introduction, it says that it is well known that it is impossible to define equality between arbitrary functions. However, there is a large class of functions for which we can determine equality, and it's strange and surprising. We explore this idea using the Swift programming language. So what does this first sentence mean? This first sentence is about something that's called undecidability. If you attempt to write a program in Swift or in any other programming language that takes two functions as an argument and returns whether these two functions do the same thing, it's impossible to write such a program. It's called, I think the name is the theorem of indecidability. I'm not sure how you say it in English. I think it's that. That's where you say it. And basically, it means that some ideas that we could have, it's not possible to write a program that implements the idea. The most common example is the halting problem. So the fact that it's impossible to write a program that tells you whether or not another program finishes or loops forever. That's true in the general, how do you say it? In the general use case, in the general like kind of program that we write. But as we'll see in this article, it isn't true when we restrict ourselves to some very specific types, to writing functions that operate on very specific types. So let's see more what it's about. So Brandon is saying that he spends a lot of his time trying to find new and creative ways to bring seemingly complex functional programming ideas down to earth and make them approachable to a wider audience. He does this while creating episodes for Point 3 and when working with clients. And after this, when creating TCA, but this article predates the creation of TCA, there are a lot of wonderful ideas in functional programming that can be understood by everyone and can help everyone's day-to-day code make everyone's day-to-day code more extensible, transformable, and testable. A great example of this would be, for instance, the map function that I would say most or even all Swift developers have become accustomed to using, which is the map function does come from functional programming. However, I want to take a break from all that and discuss something completely impractical. There's very little chance you will use this in your everyday work, I've warned you, but it does give us an opportunity to explore a strange and surprising result in computation and mathematics. It can help show that the connection between the two topics is perhaps deeper than we may first think. Sorry, I've eaten just a bit before the live stream, and it's never a great idea to eat before you're about to speak a lot. So to show this, we are going to be implementing seemingly impossible Swift programs. That is, we are going to implement some functions in Swift that, for all intents and purposes, should be absolutely impossible to implement. In fact, the mind kind of boggles when confronted with the implementation because it seems so outlandish and outside the realm of reality. Having read what comes after, I can tell you, when I came back to it this week to this article, I was like, whoa, this is so hard to wrap your head around everything we're about to see. None of the results in this article are original material by me. I learned of these ideas in a series of papers and articles. References are at the end. The only thing original in this article is the presentation of the material in a hopefully approachable way, as the papers can be quite dense. All of the code in this article is available in a gist on GitHub that can be copied and pasted into a Swift playground if you want to follow along at home. And we're going to build the code in the playground as we go during the live stream. So the article was based on this article is based on other research papers to make them more approachable, and this live stream is trying to make that even more approachable by making it accessible on YouTube. So it's a whole chain of trying to talk about this very complex idea. So first, let's talk about completely possible programs. Let's start with something simple and very much possible in Swift. As of Swift 4.2, so a few years ago indeed, the standard library has a function allSatisfy that allows you to run a predicate on every value in an array and determine if the predicate is true for each element. Before we go further, I just want to define the word predicate because when you're new to computer science, you might not always know what it is, as it's a word that comes mostly from mathematics. A predicate is simply a function that returns a Boolean. It's nothing more than that. So this is a predicate because it's a function that takes arguments and returns a Boolean. Same thing here. So really, whenever you read predicate, you can mentally replace it by function that returns a Boolean. It will mean the same thing. I see a question about the future of iOS native development market. I'm sorry, I'm not going to answer it because I'm not sure. Honestly, I don't have a good point of view. I only know like a small part of the market in France. So I'm sorry, but I just don't have the knowledge to give a good answer to this question. So we have two examples in the code. So actually, let me copy that and go to Xcode and start pasting. So I created a playground, which is always a bit of a challenge when you do a live stream because playgrounds are prone to crashing. So we'll see if it works as expected or not. So we can see here, indeed, it returns false. Here, it returns true. Oh, right. Let's go back to the article. So allSatisfy, what it does, as the name suggests, is that it calls the predicate over all of the elements in the array. And if the predicate is satisfied for all of the elements, meaning when you call this function by passing the values in the array as the argument of the function, the calls all return true, then allSatisfy itself will return true. So allSatisfy, it does a logical end between all of the calls. And if you studied logic, you might remember the quantifier for all when you say this statement holds true for all value in that set. It kind of like captures the same ID. And there is a dual version of this operation that checks if any value in a collection is satisfied by a predicate. So this is the exists quantifier in logic. The standard library calls this contains for historical reasons, but let's redefine it to give it a better name. So calling it any satisfy. So let's paste the code into Xcode and let's have a look at it. so an extension on array. And any satisfy also takes the predicate right here. And what it does is that it also iterates over the array. But this time, as soon as it finds one element for which the predicate evaluates to true, any satisfy returns to true. So we can really see it. All satisfy, it's a logical end between all of the calls of the predicate over all of the values of the array. And any satisfy, it's a logical or, 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 so like, just let me write it, this one, between the calls of the predicate over all of the values of the array. Although the implementation of this function is quite simple, it's still more complicated than it needs to be, because any satisfy can be defined in terms of all satisfy. This is given by the so-called De Morgan's law, which might bring memory if you have studied logic, which says that the negation of a disjunction is the conjunction of the negations. It's a bit complex, so let me explain the vocabulary. So disjunction means or, and conjunction means and, and what it means is that if you take the negation of and, if you take the negation of or, then it's the negation of the left operand and the negation of the right operand. And I think it also works the other way around. And in particular, negating both sides of this equation, we see that A or B is the same as not A and not B. This says that any of A or B is true is equivalent to the negation of all of A and B are false. So we can re-implement any satisfy using this observation. So let me update the code in Xcode. And so what it says now is that any satisfy is the same than not satisfying the opposite of the predicate. So it's like, since any satisfy is true if it's true for one element, then if the opposite is, you can see the mind-boggling is starting to get me. So trying to phrase it correctly, it's like, if the predicate is false for all of the elements, then any satisfy is also false. And it's basically building upon that. So these programs are completely possible to implement today in Swift, and so there is nothing too surprising here. And the reason, maybe it talks about it in the article after, but the reason why it's possible to write these programs is because the array has a finite number of elements, and the keyword here being finite. Now let's start to approach impossible programs. So now let's construct some functions similar to all satisfy and any satisfy, but that will naturally lead us down a road of impossibility. What if we wanted to check that a given predicate evaluates to true for every value inside some type? That seems pretty hard, so let's start with some small types. For example, bool, which only contains 2 values. So I'm gonna copy and paste the code back into Xcode. So we have our extension of bool, we have all satisfy, and you can see that for a predicate to satisfy all of the values of bool, which are true and false, the predicate must evaluate to true when you pass it true, and also evaluate to true when you pass it false. So for instance, all satisfy $0 equal true is false, because it's not true for all the possible values the Boolean can take. Same thing for always being false, but on the other hand, saying the predicate $0 or not $0 is always true, because for true, it's true because this one is true, and for false, it's true because the right side is true. So let's see where this leads us. So since bool only contains 2 values, we can simply evaluate the predicate on each of its values and confirm that it is true for both. We have the same idea of bool containing a finite amount of values. Using this function, we can clearly see that indeed not every boolean is equal to true or false, but every boolean or its negation is true. More generally, Swift 4.2 has a protocol called case-iterable, which allows types to explicitly enumerate all of their values. You've probably used this protocol when writing enums. All of those types could also carry this function. So let me also put the code into Xcode. I'm going to run the code also, just to make sure that we indeed get the value that we are supposed to get. So here it does the same thing. It uses the fact that case-iterable produces this static all cases array of all the cases in the enum, and then calls all satisfy, passing the predicate as an argument. To test this out, we will define a direction enum for the 4 cardinal directions, and then verify that certain properties are satisfied for all values in the type. So we have a bit of code here. Let's paste it into the playground. So we have the enum direction with 4 cases, up, down, left, and right. It conforms to case-iterable, and we can see we also have 2 computer properties, rotated left, which rotates the direction to the left, so counterclockwise, and rotated right, which rotates it clockwise. So up becomes right in that case. And then we're calling on direction, all satisfy that they are all cases are up, which is of course false. And it seems that saying that for all values, if we rotate left and then rotate right, so we like cancel the first operation, then we should go back to the initial value. And this one should evaluate to true, which is indeed confirmed, as you can see. And once again, it works because the enum contains a finite number of values. So the article says that here we see that indeed not every direction value is equal to up, but if you take any value and rotate left and then right, you get back to where you started, and we have verified that property holds for every value in the direction type. So this is like if we could write the same kind of code for integers, that would be extremely useful when writing unit tests. Spoiler alert, it's not possible. So we've now seen that it's possible to sometimes ask an entire type to check if all of its values satisfy some predicate. In particular, we could do this for bool and case-iterable. Now we move on to these impossible programs. Now let's try to generalize the examples from the previous section to see how things bring us into the land of impossibility. What if instead of asking bool if all of its values satisfy a predicate, we asked int? So this is the kind of code we would like to write. Of course, we can't run it because we don't have an implementation for all satisfy, for int. But for instance, asking if for all ints, this is asking if all ints are even. So if the remainder of the int when divided by 2 is equal to 0. This is saying whether all integers are strictly greater than 0, which should be false. Same for the first one, but there's no way to check for now. And the last one is about checking if for all integers, either the integer is equal to 0, or strictly less than 0, or strictly greater than 0. And this one should be true because we are covering all cases. If we are able to implement this function, then we'd expect the first 2 invocations of it to return false, because certainly not all integers are even or greater than 0, but the last one should be true, because indeed, every integer is 0, positive, or negative. It could even be a XOR, because you cannot be 2 at the same time. However, we cannot possibly implement this function. Int holds way too many values for us to possibly be able to check each one against the predicate in a reasonable amount of time. It's best to think of int as modeling the infinite set of all integers. This comment is because we know that int still holds a finite number of values, which is probably like, the number of values it can hold is 2 to the power 64, I guess, these days, and it ranges probably from like minus 2 to the power 63 to 2 to the power 63 with some plus or minus equal 1 thrown in there. but the number of values is 2 to the power 64 in total, which is quite a lot, and not something that we can iterate over in a reasonable time. So we stop there. We could also try implementing this for large types, like string, for instance. So if we had a function all satisfy on string, we could test, are all strings equal to cat? This should probably be false. Do all string have a count strictly greater than 0? Also should be false, because there is the empty string that doesn't have a count strictly greater than 0. And do all string have a count that is greater and equal to 0? This one should probably be true, because normally a string shouldn't have a count of -1. Again, if we are able to implement this function, we'd expect the first invocation to be false and the last one to be true, but this function is impossible to implement. String contains infinitely many values, and so there is no way we could possibly check them all against the predicate. And here it's even worse than for int, because a string is not bounded in its length. So a string can have more than 64 characters, whereas an integer is limited, an int is limited to 64 bit digits. We have finally come face to face with impossible functions, but actually impossible, not just seemingly impossible. These functions can never be implemented, and indeed their implementation is equivalent to the halting problem that I mentioned at the beginning. These functions may seem silly at first, but they are connected to a very real problem of determining if two functions are equal. For if we could implement the above functions, then we could implement equality between, say, functions from int to int. So we could define an equal operator that would take two functions from int to int, and it would return whether or not these two functions are equal, meaning that for the same value, they return the same output. For the same input, they produce the same output. For the same input, they produce the same output. And you would implement it quite naturally by doing int all satisfy, that when calling the left-hand side, so the function on the left-hand side with an integer, you do get the same result than when calling the function on the right-hand side with that same integer. This is yet another impossible function to implement, and also equivalent to the halting problem. So we've seen possible programs, we've seen impossible programs. Now let's go into the meat of the article, which is seemingly impossible programs. So now that we have surveyed the possible and impossible for implementing a certain type of function, let's look at something that should be possible, yet somehow is not. Consider the following types. We have an enum bit with two cases, 1 or 0, and then a struct bit sequence where we have a function at index which allows us to read the value of a bit at a given index. So I'm going to copy and paste this into Xcode. I'm gonna remove this part because I cannot implement it and it will just add a compilation error. Okay. So bit is a simple type that holds two values, and bit sequence is the type of functions from non-negative integers into bits. The reason it is called bit sequence is because it is kind of like an infinite sequence of bit values in which you are able to ask what is the value at an index using the @index method. In this interpretation, it is best to think of uint as the infinite set of non-negative integers. Once again, because uint is still limited in the number of values it can hold. We can easily define values of bit sequence by just providing a closure to map uints to bits. So, for instance, we have a first sequence called x's, which is always 1, another one called y's, which is 0 if the index is less than 1000 and then 1, and then another called z's, which is 0 when the index is even and 1 when the index is odd. And we can see if we call x's at index 0, 1, and 2 always 1, y's at index 0, 1, and 1001, 0, 0, 1, and z's at index 0, 1, 2, 0, 1, 0. Let me put this code in Xcode. Let me also build it so that if there is an issue, we can find it at the right time. Okay, seems like everything is in order. And although we cannot concatenate two infinite sequences together, we can prepend a new head onto an existing sequence. So for that, we're going to overload the operator plus. So let me paste the code and try to comment it. So with plus, we can prepend a bit onto an existing sequence, and it returns a new bit sequence. And we do it by creating a new bit sequence, and the closure that defines this sequence says that if the index is 0, then we return the bit we are appending. Otherwise, we read the bit sequence on the right-hand side, and we shift the index by 1 to the left. So it's quite a natural way to prepend, so to add a value at the beginning of the sequence. And we can see if we create a new sequence W's by adding a 0 at the sequence X's, which was all ones, then when we run the code, we have 0 at index 0 and then 1 at all subsequent indexes. So the bit sequence type holds infinitely many values. In fact, it holds an unconscionable number of values. It has more values than string does. It holds so many values that it cannot be counted with the natural numbers. So here there is a link to uncountable sets that I will not go over, but if you like math, you can try and go over it. I want to go back to the article. Where was I? I should have done a command click not to lose where I was. I think I was here. I was here. And I see a comment. I would omit return on line 79. Haha, this is so you're right, but this is a product of its time because this code is from December 2018. So Swift 5 wasn't there yet. And so when the code was written, you had to write this return. But now, indeed, since there is only one statement in the one expression in the function, we can omit this return keyword. That's a good remark. Let me go back to the article. Okay. So I stopped here. So it's an infinity that is even larger than the infinitude of natural numbers. It's so large that it can hold an infinite number of disjoint copies of natural numbers inside of it. Don't ask me why, as I told you in my initial disclaimer, I've never really studied this part of math. So given how massive this type is, it might be surprising to learn that we can define inSatisfy and allSatisfy on it, and these functions will terminate in finite time. That means we can exhaustively search the very large infinite space of bit sequence in finite time. Even more, we can implement equality between functions on bit sequence. So we can implement an equal operator that will say whether two functions operate on a bit sequence are the same. I see some other comments on these return keywords, which I guess do seem a bit weird when you've gotten accustomed to writing Swift UI code and writing like post Swift 5 code. So surely this must be impossible to write such a function. How on earth could we expect to determine the equality of two functions whose domains are not only infinite, but a size of infinity that is difficult to even grasp? If you followed from here, you might remember that if we can define allSatisfy, then defining this equality here is a consequence from it. So actually the question is not how can we implement this, but how can we implement this? And the two are actually like kind of equivalent, or maybe exactly equivalent, I'm not sure. So how can we achieve the seemingly impossible? Let's take it one step at a time. Let's first see if we could define an allSatisfy function on bit sequence. So extension of bit sequence, a function allSatisfy which takes a predicate that operates over a bit sequence. This function definitely answers the question of whether a given predicate evaluates to true for every value inside bit sequence. Well, this seems difficult, so let's kick the can down the road and appeal to a hypothetically defined anySatisfy by using De Morgan's law again. So remember, if you've implemented allSatisfy, then, or rather, if you've implemented anySatisfy, then implementing allSatisfy is just a matter of using anySatisfy under the hood. So this would look like this. We've seen it before in the article, this example. So now we just have to define anySatisfy. So let's get the signature up. Very similar to all satisfy, as you can see. This seems just as difficult as all satisfy. So what have we gained? Well, let's introduce a tiny twist. Suppose there existed an hypothetical find function such that when given a predicate on bit sequence, it would find a bit sequence that satisfies the predicate. And if no such values exists, it would just return any sequence, the contents of which don't really matter. Let's write the signature of such a function. So it would be called find. It would take a predicate and return a bit sequence. So you can see it's very similar to any satisfy, except that from a bool, we are now returning a bit sequence. What's interesting is that they say it would find a bit sequence that satisfies the predicate, and if no such value exists, it would just return any sequence. How do you distinguish between the two return types? So if such a function existed, then we could implement any satisfy in terms of this find function by doing any satisfy is calling the predicate. So it's calling find a sequence that satisfies the predicate and then checking that it does satisfy the predicate. So this function returns something that may or may not satisfy the predicate, but if it finds something that satisfies the predicate, then we know that we found something. So we first find a sequence satisfying P. If it exists, and I'm going to redo it. We first find a sequence satisfying P if it exists, and then feed it into the predicate P. This means that if it does exist, we'll get true, and if it does not exist, we'll get false, just like we expect. It probably feels like we're just kicking the responsibility even further down the road without accomplishing anything, but we've now boiled down this seemingly impossible program to implementing the find function. So we wanted to implement all satisfy, then we said, okay, we can implement all satisfy if we have any satisfy. Then we said, okay, if we have find, then we can implement any satisfy using find. So now we just need to implement find. So how can we find a sequence satisfying the predicate P? It turns out we can actually construct it recursively. For, say, there exists a sequence S such that the larger sequence 0 plus S is satisfied by the predicate, then we can peel a 0 of this hypothetical sequence and continue our search on the tail. And if no such sequence exists, we can try the same process but using 1 instead. So let's give it a shot in code. So I'm going to start writing the code that I haven't written in the playground. So first here, the extension that implements all satisfy in terms of any satisfy. Then the one that implements any satisfy in terms of find. And finally, this implementation of find. So what does it look like? We say, okay, if bit sequence any satisfy, so what is this S here? Okay, it's, so we say if in bit sequence, what's interesting is that we use bit sequence dot any satisfy, but any satisfy itself is defined in terms of find. So we say if that's when we get to the really tough part of this live stream. So if there is a bit sequence, if there is in bit sequence a sequence that satisfy the predicate and starts with a 0, then we can return this 0 and do a recursive call by saying find with a new predicate where we have already fixed the 0. Not sure about that I understand what this does. Otherwise, we try the same, but by adding a 1. Let's go back to the article, maybe it will help us. So this compiles in Swift, but it's really mysterious. Is there any reason to believe this function will ever terminate? Because we are indeed calling anySatisfy, which itself calls find. Not only does it recursively call itself, so here it calls itself here and here, but it also calls anySatisfy, which also calls find, what I was mentioning. In fact, Swift is giving us a warning to let us know that this isn't quite right. As of Swift 4.2, the compiler can prove that all paths through a function will call itself, hence never terminate. So let's see if we get, yes, we have the warning function call causes an infinite recursion. We need to introduce some laziness into our function so that we do not try to compute everything at once, but instead compute only as much as we need. The recursion calls to find happen in each of the if-else branches and happen to the right of the concatenation operator plus. In order for this function to ever terminate, you would need that at some point the right side of plus does not need to be executed anymore. So we can lazily defer that by making the right side of plus an auto closure. So we only evaluate the sequence if we actually intend to use it. So let me update the code here. So it does the same thing, it just makes the sequence, instead of having a bit sequence, we have a closure that produces it, and it is an auto closure. So we just pass a sequence, but it gets wrapped into a closure. This way, if we fall, the idea is that if we fall into that side of the ternary operator, so if we return only the left-hand side, then we don't need to actually evaluate the sequence. We only evaluate the sequence when we actually need to use it. So it looks a little uglier, but now it's lazy and the Swift warning went away. So let's check. We just have another error about escaping closure, captures not escaping parameter p. I guess we'll need to add this as escaping here. So the warning went away. However, there's still a recursive call happening that will never terminate. And Swift cannot yet detect this one. In order for find to do its work, it needs to call out to anySatisfy, but then anySatisfy immediately calls find again. We have to make anySatisfy less eager by hiding some of its work inside a closure. Rather than calling out to find directly, let's construct a whole new bit sequence that calls find under the hood. So we change the code of anySatisfy. So I'm going to paste it just below for now so we can compare the two. So before we would just call the predicate on the sequence found by find. And now we store the sequence found in a variable. So here we do bit sequence. Okay, so now we have a closure here. So we construct a bit sequence here. And the idea is that we're going to read the sequence, we're going to read it value by value instead of just passing the whole sequence, I guess. So I can remove this part right here. I have issues about escaping closure, so we need to fix a few things. Okay. This is equivalent to what we had before, but now it is sufficiently lazy for Swift to be able to run this program. It's going to seem incredible and almost magical, but rest assured there are no tricks involved. Let's take this for a spin. Let's try to find a bit sequence that satisfies the property that it evaluates to 1 on the first 5 even indices. So first, I think I need to fix a few things. So this needs to be at escaping, I would say. And here it also needs to be at escaping. Let's try and build this. I don't see any error for now, which I guess is a good thing. Okay. Nothing gets written, but there is no statement to execute. So I will take this as a sign that it's working and I can go back to the article. So this is the code we're writing. So we want to find a bit sequence such that its first 5, so that's at index 0, it has value 1, same at index 2, same at 4, same at 6, and same at 8. So let's try and do that. Okay, so it did find a bit sequence, now how do I print a bit sequence? Maybe we're going to see that just after, so I'm not going to start writing the code by hand just now. Yes, we have the code here. So this is incredible, but in finite time, we have searched the entire infinite space of bit sequence values and constructed an instance that satisfies the predicate we provided. Don't believe it. Let's evaluate it to verify. So here we have found something, but we could argue that the fact that we have one instance of code where we do find something doesn't mean that if we had asked for something impossible, it would have also found it. Like, what if we had asked for a sequence such that at index 0 we have 1 and at index 0 we have 0, which is not possible. But I guess we're going to see that. Yeah, we're going to see just after. So first I'm going to print this sequence the best way I can, and we can see, so 1 0 1 0 1 0 1 0. So it seems to be 0 is 1, yes, 2 is 1, perfect, and then it's just zeros. And we could see that it took some time to run, so it gives us an idea that we are doing like some kind of not exhaustive but expensive computations. So we can also ask to see if every bit sequence satisfies some predicate, or if any bit sequence satisfies every or any. Yes, so we can ask to see if every bit sequence satisfies some predicate, or if any bit sequence satisfies it. For example, being both 0 or 1, or being always 0. So let me run this code, and I want to also experiment a few other things. So here we say that at a bit sequence is either 0 or 1 at index 0. Okay, that's true. And here we say that we are asking whether all bit sequences return 0 for their index 0, and that's false. Okay. I'm gonna try to do like bit sequence dot all satisfy. So s in, and I would say s dot at index of 0 equal 0 and s at index 0 equal 1. That one should return false, right? Let's try it. It does return false, and quite quickly, because I guess it's very easy to find. That there is no. That's interesting, because the fact that it managed to say false means that it managed to prove that there is no such sequence. And so, as soon as it had found one sequence that didn't verify it, it could stop there. It could stop the search. And so I guess it just had to take the first sequence that either had 0 or 1 for index 0 to see that it didn't satisfy this predicate. And then I wanted to say, okay, let 1 and 0 on first. And so I'm going to do bit sequence dot find s in like that, and I'm gonna say s at index 0. So I'm gonna do the same. Should have just copy pasted like that. S no, like that. S dot at index 0 equal 1, something like that. What's it going to do? So it still returns a bit sequence, but in that case, I guess it returns like just like anything. And then I would need to evaluate the predicate on this, because so here, that's what it does. Like it evaluates then the predicate on the bit sequence. So if here I still take like this and I call it passing what doesn't it work? Maybe I need to do like something like that. So it does return false, and like I'm gonna call it like is for real, like is it a real thing or not? And indeed it's false, because find has returned a sequence, but that doesn't satisfy the predicate, and so it doesn't work. Okay, let's go back to the article. So in the first expression, we have determined that every bit sequence satisfies the property that its first value is either 0 or 1. In the second expression, we have determined that not every bit sequence has its first value equal to 0. Another example, so here, bit sequence ain't satisfy, so trying to find a sequence that has the same value at index 4 than at index 10, and normally there should indeed be such a sequence, so this should return true. We can see that this is costly. I'm going to comment out this part so it runs faster. And indeed, this is true. So here we have successfully verified that there is at least one bit sequence whose fifth value is equal to its 11th. Remember, the sequences are 0 based, so plus 1. We can keep going. Now that we have the all satisfied function at our disposal, we can define equality between functions that have bit sequence as their domains. So remember, if you have all satisfied, then implementing equality between functions is rather straightforward. You can see that we just need to add the extra at escaping attribute, but we say, what does it mean for two functions that operate over a bit sequence, so whose domain are bit sequence to be equal? It means that for that all bit sequence satisfy that calling the function on the bit sequence on the no. What does it mean that two functions that operate on bit sequence are equal? It means that for all bit sequence, calling the left function on a sequence yields the same result than calling the right function on that same sequence. That seems more correct. Okay. This is able to deterministically and in finite time determine when two functions on bit sequences are equal. This is completely impossible to do with ints and strings, but here we have done it for bit sequence. So let's give it a spin. I see, Leven, you're saying when I watched live but came late, don't worry, there will be a replay as soon as the live stream is over. So let's give it a spin. So I'm copy and pasting the code. So here we have a first function that operates over a bit sequence and always return 1, and another one that always return 2. And we want to test whether const 1 is equal to itself, const 2 is equal to itself, and const 1 is equal to const 2. And we can see that we do get values returned by this equal operator. So here we have constructed two functions. One always returns 1 regardless of input, and the other always returns 2, also regardless of input. Clearly, these functions are equal to themselves and not equal to each other. But here we have actually computed it in real time. To come up with more complicated functions, let's introduce a helper that converts a bit value into an integer. So we have an extension on bit that's going to turn a bit into a uint and saying if it's 1, return 1, if it's 0, return 0. So it's just mapping the two cases to two integer values. With that helper defined, we can cook up some more complicated looking functions on bit sequences. So let's see what these two functions f and g's are doing. So f takes a bit sequence and returns a uint, and it takes the element at index 1, so the second element, and multiplies it by the third element. And g adds the second element to the third element. So the first multiplies second and third values of a sequence together, and the second one adds. It certainly seems like these functions are not equal, but let's check. And by equal, it means that they return the same thing for every value. It doesn't mean that the code is the same. You could have two different implementations for a same function, meaning that two different pieces of code still return the same value for a same input. For instance, you could imagine basic ID is like func double 1, which is going to take a, which is an int, and return an int. You could implement it like this. So return a plus a, and I think you're seeing where I'm going. we could implement another version of double that says a times two. Two different implementations, but still the two functions are equal in the sense that when you give them the same input, they will both produce the same output. Let's go back to the article. So we're supposed to run this code and see that f is equal to f and g is equal to g, and f is not equal to g. So adding two elements of the sequence and multiplying them is not the same, meaning that there are sequences, there is at least one sequence for which both functions don't return the same value. So we could imagine like, because for a sequence where at the index 2, 1 and 2, we have two zeros, for instance, then 0 times 0 is the same than 0 plus 0. But if there is a 1 and a 0, then it doesn't work. If there is a 1 and a 1 also, it doesn't work. So incredible, again, we have searched the infinite space of bit sequence values and determined that these two functions are not equal to each other. And it will go back to it later, but what's interesting here is that the false is actually the easiest one to, like, these functions, they really work. But if we were to fake it, the false would be the easiest one to find, because to prove that f and g are false, you need to find a counterexample. And so you could always iterate over all of the bit sequence, and you don't stop until you found a counterexample. But that means that then you will never return true. So this is not this simple implementation that is happening, because we could think, okay, yes, we just need to search the space, and then when we find a counterexample, we return false, and if we don't find one, we return true. Problem, that space is infinite. So there is something more at play here that we'll cover just a little bit later in the article that makes it that to say that these two functions are true, you don't need to search over the entire space. Searching over a finite subset of the space is enough to conclude. But I'm getting ahead of the article. So now let's introduce another function that looks a little different from f and g, so a function called h. So let's see what this function does. So h, once again, takes a bit sequence and returns a uint, and it says, okay, it switches over the second and third values in the sequence, and it says if there is a 0, if either of these two values are 0, it returns 0, and if either of these is a 1, then it returns the value of the other one. Do we think this function is equal to either f or j? So let's try to see what Swift has to say. H is equal to h, that stands to reason, and we learn that h is not equal to g, but h is equal to f. So this implementation here is the same than this one in the sense that it will always return the same output for the same input. So it seems that h is equal to f, and indeed, if we look at its definition, we see that we always return the non-zero value from s at index 1 and s at index 2, and 0 otherwise, which is equivalent to multiplying bits together. So this was basically multiplication being implemented for each possible case when you are in a discrete case, like bit is, because it's either 0 or 1. So let's try one more function, but something a lot more complicated. So this function k, it takes the second element, adds it to the third, adds 908, then takes the remainder divided by 6, and divides the whole thing by 4. Is this function equal to any f, j, or h? We have no idea because it's so complex, but with the code we've written, we can affirm that k is the same than f, so the same than multiplication. So meaning that this will always yield the same result than this. It's not equal to j, it's equal to h, which makes sense because here we saw that h is equal to f, and equality should be transitive, and k is equal to itself. So that's fascinating. It seems that somehow k is equivalent to both f and h, even though it has a widely different implementation. How is this possible? Now we get to the actual explanation behind the magic trick. The only thing better than implementing a seemingly impossible function is finding out that the explanation of its existence is deeply rooted in mathematics that have been known since the late 19th century. Although we cannot give a full treatment of this topic, we explain some of the concepts and how they all fit together at a very high level. I try my hardest to draw a narrative line from the mathematics to what we just witnessed in this Swift code. But it's more of a story than a rigorous exposition. So it all begins with a field of mathematics known as topology, which is a study of topological spaces and their properties. Intuitively, a topological space is an object that comes equipped with a notion of when points in the space are near each other. The rigorous definition of topological spaces is far more abstract and at first glance wouldn't seem connected at all to what we just described. Just as in programming, we see that functions between types tell us a lot about the types themselves, such is true of functions between topological spaces. However, we can't allow just any such function. We want those functions that preserve the structure of the space. And for topological spaces, that means the function preserves the closeness of the points. Again, the rigorous definition looks nothing like what we have just described, but it is indeed the very general definition of continuity, and in fact, subsumes the definition of continuity that you may have learned in calculus. So the idea is that if inputs are close together, then outputs should also be closed together. Now that we know the basic objects we are studying, topological spaces, and the function that we allow between them, continuous functions, we want to understand their properties. Topological spaces in the large are varied and wild. There is a subset of spaces that have some nice properties called compact topological spaces. Intuitively, these are spaces that have a kind of finite quality about them, and for many intents and purposes, behave like finite sets, even though they can have infinitely many points. Already, we are seeing sea shadows of our problem in the math, for we are very interested in infinite sets that have finite qualities about them. Do we say infinite and finite, or do we say infinite and finite? Yeah, because we don't say infinite, so I'm just wondering about pronunciation, but I guess you do say infinite and finite. And the two don't pronounce the same, which is a bit weird. I see a question in the chat. What are we talking about? We are talking about an article whose link is in the description about how you can implement functions, programs that should normally be undecidable when you implement them for some very specific spaces. Okay, we stopped here. We also want to know of some nice subsets of continuous functions, for even though continuous functions seem to be well behaved in that they preserve closeness of the points, there are still some truly wild examples of them. So I want to see what is the wild example. Oh yes, Weierstrass functions, which is this weird function which I think is like continuous everywhere but not differentiable anywhere. So it's like it's moving in a very weird way. And I haven't studied math recently to remember to have anything else to say about it. But the thing is that there's a subset of continuous functions not known as uniformly continuous, and they have a lot of nice properties. Intuitively, these are the functions that not only preserve the closeness of points, but the closeness of the points in the range of the function doesn't depend in the location of the points in the domain. That is, we get to control the closeness of points in a uniform manner across the domain of the function. It can be shown that every uniformly continuous function is continuous, but not vice versa. Hence, uniform continuity is a stronger property. I think there is a nice example visible here. So the idea is that the function is continuous, but you can see that the way it increases is also bounded in the sense that if your input values have a range of, say, like 4, then you know that the range of the outputs will not be more than k times 4. And this k is a characteristic of the function. But once again, I haven't studied this in a long time. And I think, yeah, what I call k here is what they call maybe this like delta here. Let's go back to the article. So once you know of the object and function you are playing with, and some nice subsets of those things that are well behaved, you want to start proving some theorems. An important theorem for our seemingly impossible functions is stated as such. If X is a compact space and Y is any space, then every continuous function from X to Y is uniformly continuous. This is technically only true for a subset of topological spaces known as metric spaces, but the detail is not important for this lay description. This is a very powerful theorem. It states that even though it is far from true that continuous functions are uniformly continuous, if the domain of the function is compact, then both types of functions coincide. Continuous implies uniformly continuous. And I guess this is this property of uniform continuity that allows us to search an infinite space in a finite time. And so I remember this is the part of the article that I had to like wonder over it the first time I read it to like put all of the pieces together. But the idea is that since in a uniformly continuous function, you know that points that are close together will not go that far away when the function is called, I guess somehow it has the consequence that when you're trying to find a sequence that satisfies a predicate, you know that once you have looked into all of this subset of a bit sequence, then you know that you won't find it anywhere else. I guess it's the same idea, but to be honest, I have a hard time like putting all of the pieces together, and I don't feel like I have a complete picture, a complete like mind picture of how it works. So now about computation. So now that we have some topological results at hand, the question remains how to apply this to programming and the Swift programs we constructed above. It turns out there is a very deep and far-reaching connection between math and computation, known as the Curie-Howard correspondence. Its roots are in constructive mathematics, and it roughly says that any proposition in constructive mathematics can be translated into a type, and any proof can be translated into a value of that type. Constructive mathematics is a weird subject. It's like classical mathematics, except that it does not allow the law of excluded middle or double negation elimination. This means that a lot of proofs in classical mathematics, it says mechanics, but I guess it's classical mathematics, are not valid in constructive mathematics. And some theorems are just plain not true. In particular, in constructive mathematics, it is true that every constructible function is continuous, which is definitely not true in classical mathematics. So let's tie the knot. And as we are now able to tie our stories of topology and computation together, it can be shown that the bit sequence set is compact. In fact, it is equivalent to a well-known object called the Cantor set, which is constructed by taking the unit interval of real numbers and recursively removing the middle third from it, and all subsequent subintervals. After taking the limit of this process, you are left with all the numbers between 0 and 1 whose ternary representation contains only zeros and 2's. Now that we know bit sequence is compact and that all functions on it are continuous, we can apply our theorem to know that all functions on bit sequence are even uniformly continuous. This means that although bit sequence is infinitely large, functions on it are determined by their behavior on a finite subset of bit sequence. The size of that finite set is known as the modulus of continuity of the function, and all of these results together explain why we are able to achieve the seemingly impossible by exhaustively searching an infinite space in finite time. And so, this modulus of continuity is this value I called k before, is this thing here, which says that if you look at the values, for instance, I don't know, like between 0 and 5, then the distance between the outputs is going to be less than, for instance, 10 times 5. So it's going to be less than 50. It's this thing that you can see right here. And so the way I understand it, the way this modulus of continuity applies is that if we go back to the code, since here, you see, I'm going to run the code, and you can see that here it computes. I want to show you like how fast it computes here. Because the way I understand it is that if you're writing functions that only operate on small indexes, it's going to be faster to run than if you operate on indexes that are further away. Because when you add, or rather, when you use indexes that are far apart, then the module of continuity of your function is also increasing, and the module of continuity is probably proportional to the execution time. Okay. There is always a time where the playground is going to crash when you run a playground. Okay. It's so slow, but I don't remember it being like that slow last time. I'm just going to stop it and just relaunch it. Or maybe I will just comment out some code because maybe there is just like way too much code. It seems like it's completely stuck. Let me stop it. Okay. I think it's time for me to reopen the playground. Let's see. I hope it runs again. It's crazy that it's stuck at the same place, even though like I didn't dream it, like it was working correctly before. Maybe there is some code that I added. Or if I just run it up until this part. Okay. So it seems like it's here that it's starting to be like unhappy. Because if I run it up until here, you know what? Actually, I'm gonna kill Xcode completely. Okay. And now I'll reopen the playground. And I'm gonna be like finger crossed now it works. Let me relaunch it. I knew it that when I was using a playground in the live stream, at one point or another, it was bound to lead to trouble. Okay, so it seems that there is really like something here. You know what? I'm just going to comment out. I don't know. Is it this line that causes an issue? Okay, it seems like this line was indeed taking a bit of time, but you know what? That's kind of interesting. I'm just going to take this here. Okay. Because you see here we have 4 and 10. So I'm going to do 4 and 6. Okay. Then I'm gonna do 4 and 10. And then I'm gonna do 4 and 20. And normally, as I increase the range between the indices that I'm using, I should see that it takes longer to run if I'm correct. We can see here it's longer, and here it's even longer. And I guess since so this module of continuity is a number, so this means that like the complexity of the algorithm should be linear, but maybe it's linear with a very, very, very big coefficient, because here with 20, it seems to take a lot of time. So what I wanted to get at is that it's not because we can indeed search the infinite space in finite time, that this finite time is reasonable. Maybe this finite time is extremely big, and it's so big that while it's theoretically possible, it's not practical in any real use case, because we can see that when we look at like simple cases where there is only like a range of 2 between the indices we use, it works fine. But as soon as we get to like 16, it no longer works. And so that means like you have 16, it means you have what, like so 2 power 1 is 2, 4, 8. You have like 4 bits of range. That's like half the power of the first Nintendo Entertainment System, to give you an idea, or half the power of the first Game Boy, which were 8-bit consoles. So even though it's possible, maybe it couldn't be like practical to use it. That's what I wanted to get at. So this like finite time, we don't know how long it is, and we don't know the complexity of it. So conclusion, we've reached the end of this article. So we've now accomplished what we set out to: construct a seemingly impossible Swift program. We were able to exhaustively search an infinitely large space in finite time and answer the question of whether two functions were equal at every point. In doing so, we not only uncovered something that seems to defy reality, but also can be explained in a very concise way by mathematics that has been known for nearly 150 years. And although these techniques and results aren't necessarily useful or practical for everyday Swift programming, I hope they can give you a sense of how the effectiveness of mathematics in computing, to know that math has been able to produce such a counterintuitive result and give such a concise explanation of why it is the way it is. I begin to feel that I can trust mathematics as a guiding beacon for how programming can be done well. This is why I feel strongly that simple mathematical constructs like pure functions, monoids, etc. form a strong foundation of abstraction, as opposed to the overly complicated and often ad hoc design patterns we see in software engineering. We've reached the end of the article. There is just one last question that I feel the article doesn't cover, and I would like to try and offer my explanation, which, remember, might be wrong. It's about the fact, why is this possible over bit sequence, and why isn't it possible over the integers? And my understanding of it, or rather like the intuition I get, is that we saw that if you want to combine 2 bit sequences together, the operation we could implement actually was we could add something at the beginning. We did it. Where did we do it? We did it here. We could imagine also adding 2-bit sequence together. We would need to have a rule for the. Could we actually add 2-bit sequence together? Because if it's 0 at the same index, then it's 0. It's easy. If it's 0 and 1, then it's also 1. It's easy. But if it's 1 and 1, we need to carry it over to the next one, which means like kind of like appending, but we can only prepend. So my intuition of why this mechanism works on bit sequence and not on integers is because you cannot really define arithmetic operation on bit sequence. And so since you cannot define arithmetic, you cannot compute all the things you can compute with integers. This means that a bit sequence is in a way simpler than integers, and from that simplicity we get this extra property of being searchable in finite space. That's just like my intuition when seeing the thing. I might be wrong, I might be incomplete on it. I just wanted to share it as we finish this live stream. So it's indeed the end of this live stream, the last one before Christmas. I hope you've enjoyed this kind of like spin-off on my channel of trying to talk about something that I remembered from a few years ago, and I remember to be quite interesting. I hope you've enjoyed discovering it. As I promised in the beginning, I don't think you will use this in your real world coding, but as the conclusion mentions, if it gives you confidence that using mathematical approaches when defining your code is a good beacon, I think it's already a nice achievement. And as we get near the end of the live stream, I just wanted to say, so my live stream 2 weeks ago on an introduction to the composable architecture was quite popular. If you remember the tutorial I covered, I had 2 parts. I only did the first part. I didn't do the second part about navigation. I'm gonna do it in the future. I don't know when. I would like to do it next week. So on the week between Christmas and New Year's Eve. I don't make any promises, but I'm going to try and do it next Thursday. And I guess I just have to say once again, thank you for following this live stream. I hope you've enjoyed it. Have a nice holiday season. Enjoy your vacation if you're taking some. And see you next time for the next live stream or the next video. Bye bye.